Hello and welcome to a short video on one of the problems that we discussed in the PMO training yesterday. And this question is based on the 2022 PMO Area Stage, which states, let f of x be equals to x squared plus 3. How many positive integers x are there such that x divides f of f of f of x? I'll give you time to pause and try to find the answer. So the answer here is 6. How did we get such answer? First of all, let's first find the polynomial version of this function. So, as stated, f of x is equals to x squared plus 3. So, we already know what's inside this one. It's x squared plus 3. Okay, so now we've got this. Now to continue on with this regression, we will also use this as our x, making it x squared plus 3 squared plus 3. And this will be inside of f of x. The resulting polynomial will give us x raised to 4 plus 6x squared plus 100 plus 12. And this is still inside f. And now I will not show the computation for this, but eventually you will reach this polynomial. So now you will reach this polynomial when you evaluate this. And now the question is asking, how many positive integers are there such that x divides f of f of f of x? So what it's trying to say is that how many numbers of x divides this expression. The key idea here is the remainder theorem. The remainder theorem states that the factors of a polynomial can be found by using the highest degree coefficient factors divided by the lowest degree coefficient factors. What it's trying to say is that if you go look back in this long polynomial, the biggest coefficient, the highest degree coefficient is just 1, and the lowest degree coefficient is 147. The factors of this expression can be found by finding the factors of 147. Can be found by using the factors of 147 and 1. 1 can be either -1 and 1, and 147 can have multiple factors. But right now, we're trying to find the answer. How many different combinations? With that, let me introduce to you to a simple trick to find the number of factors. When finding the number of factors, such as 12, you have to break it down into prime factors. Prime factors are factors that are prime. In this example, there is a prime factor of 2. And then this will become into 6. Because 6 times 2 equals 12. Next, 6 can be divided into two parts, into 2 and 3. As we can see, there are no more composite numbers. There are just prime factors, prime numbers 2, 2, and 3. Therefore, 12 is equals to 2 times 2 times 3, or 2 squared times 3. So now we see that 12 is 2 times 2 times 3, or 2 squared times 3. So how can we find the number of factors in this expression? We can do it by either listing it out or a method that I will show you later. First of all, let's try to list it out. As we can see here, it can be expressed into this expression. which means we can try to group this, and maybe this. Okay, so now let's try to find the different factors of 12. We can try to group this. This will be 2 times 2. Or no, sorry. We can first use the prime factors that was already given, and it is 2 and 3. Next, we can also group this, which is 4, because 2 times 2 equals 4. Then we can do this as well. 2 times 3 is 6. And then don't forget that 12 is also a factor of 12. So we can multiply all of them by 12. And don't forget the 1, because 1 is a factor of every composite, 1 is a factor of every integer. So now that we have this, we can count them all. 1, 2, 3, 4, 5, 6. There are 6 factors. But there is a much more easier method on finding the factors. We do it by looking at the degree of each prime factor. So as we can see here, 2 has a degree of 2. And 3 has a degree of 1. What we can do is that we can multiply the degrees and add it by 1. What I mean by this is by multiplying it, we can get 2, then add it by 1, and then get 3, which is 1, then add it by 1. And then we would get 3 times 2, which is equals to 6. And as you can see here, we get the same answer. So in this example, we can try to do this method on 147, but we can use the easier method by using this. So let's break down 147. 147 has a factor of 3. We know this by adding all the digits and it will result in a 3. So 1 plus 4 is 5, plus 7 is 12. And 12 is divisible by 3. So therefore 3 is a factor. And indeed it is a factor because this will give us 49. No. And 49 is divisible by 7, which means it has a factor of 7 and 7. And now we have listed out the prime factors, which is 3 times 7 squared. So now we see that this is the prime factorization. We can finally get how many factors it has. So 3 and 7. We got 1 plus 1 times it by 2 plus 1, and it will equal to 6. That's how many factors 147 has. Take into note that we also need to take into account this one, the coefficient of 1. But we don't need to because it's redundant. We're just going to multiply it by 1. So in this, we get the final answer of 6 because by the definition of remainder theorem, we get the number of factors of x. Another way of thinking it is by factoring this expression by x. As we can see, we can remove the x in here, which will leave us, and we can remove the x in this expression, and then this will leave us this. So now, when we're trying to find x, we gotta find where we can divide this by x and it will leave a remainder of 0. We can see that here. We can see that here that x is factored out and it must be equal to 1. It must be equal to 0 so that we can say that this expression is divisible by x. So as you can see here, modulo of x, which means this will be cancelled out, this first part. So this means 147 is congruent to 0 mod x. We may not know what x is, but we both know that when it is divided to 147, it will leave a remainder of 0. So x must be factors of 147. This is where we can get the answer of 6, which is the number of factors of the said polynomial. So now looking back, what we did is by turning the expression into a univariate polynomial, and we say that it is divisible by x. Then we find the factors of 147 and we get the number of how many factors it has, which is 6. Another way of thinking it is by expressing the expression by modulo of x, and then we can cancel this, and it will leave the 147 is congruent to 0 mod x. And we don't know what x is, but we both know that that we can divide this by 147 and it will leave a remainder of 0. So we now see that it is 6. Here's my challenge for you, the viewer. Let f of x be equal to x squared plus 2. How many positive integers x are there such that x divides f of x? Okay. Thank you for watching this video, and I hope that you will be able to join my next few sessions.